Operational amplifiers. We're actually going to start with the non-ideal op-amp. And if we look, we have an input resistance, and this is node voltage 1 and node voltage 2. We have an input resistance. And this is a behavioral voltage source, and the voltage equals the open loop gain, which these curly brackets mean it's a variable, and over here it's 1e to the 8, times the voltage at node 2 minus the voltage at node 1. So far we've been doing voltage controlled current sources. This is a voltage controlled voltage source. And we also have an R out. And if we wanted, we could convert this to a Norton equivalent. But essentially we can, this kind of Thevenin equivalent, dependent on this voltage, is all that we need. So, something about this model, although it's not ideal, is that it doesn't limit the output voltage to the positive and negative supplies. Op amps, you can have a positive or minus 15 volt supply, and your output voltage can't go beyond that level. And usually it's a volt below the power, below the magnitude of the power supplies that you can reach. But still, this is a good way to start analysis. Now, these values here, where do they come from? Well, go to the data sheet. Here's the LT1001. Here's the link. And if you scroll down, you can see some of these parameters. You have the open loop gain, and here it's 450 volts per millivolt, and so that obviously, just divide that by 1 milli and you'll get the full voltage range. And the thing is you have minimum, typical, and max. And so if you're trying to guarantee something, you can use these values, the minimum value. But if you want to know what normally happens, you can use this. Now, notice that there's no RL here, but there would be an RL from out to ground. And if it's greater than 2 kilo ohms, V out can go to 12 volts, and if it's greater than 1 kilo ohm, V out can go to plus or minus 10. But notice that when the RL is smaller, the gain is reduced. And that's more than likely because RL needs to be much, much greater than, otherwise 100 times greater than R out, so that you don't have to worry about it. And so if RL is greater than 2K, 100 times less than that is 20. And that's where I came up with that number. There's other things. The input resistance here, it's 30 mega ohms. And some of these other terms about noise and bias current and offset voltages are really for more advanced classes. And so something we do to make the analysis simple is we use an ideal op amp, and we make the open loop gain infinite. We set our input resistance to infinity, and we set the output resistance to 0 ohms. The thing is if we choose our resistors, capacitors, inductors, and frequencies properly, usually these can hold true enough so that our hand calculations matches what we measure in the field. So again, ideally this would be 0, and this would be infinite. That means no current comes in and out of those nodes. And this AVOL will be infinite. Doesn't make a lot of sense here, but when we put it in a feedback system, we can get some really good mathematical operations out of this circuit.